The Earth is always moving. In fact, right now you're spinning at about 1,000 miles per hour, and you don't even feel it. But here's the question. Why does the Earth spin? This is WhyOWhyTV, where we ask the questions everyone wonders and uncover the surprising science behind them. Our story begins in an immense, swirling cloud of gas and dust, a cosmic nursery called a solar nebula. Imagine a vast, dark expanse, cold and quiet. Then, about 4.6 billion years ago, a nearby star exploded in a brilliant supernova. The resulting shockwave rippled through our nebula, causing it to collapse under its own gravity. At the heart of this collapsing cloud, pressure and temperature soared, igniting a brand new star, our Sun. But the Sun didn't gobble up all the material. A disk of leftover dust and gas continued to orbit it. Within this disk, a planetary construction zone came to life. Tiny dust grains, no bigger than smoke particles, began sticking together through static electricity, like dust bunnies under your bed. Over millions of years, these clumps grew into pebbles, then boulders, and eventually into kilometer-wide bodies called planetesimals. These planetesimals, pulled by gravity, began a chaotic dance of collision. Each impact was incredibly violent, releasing enormous amounts of energy and heat. As these pieces collided and merged, the growing mass began to spin. But why? It's all thanks to a fundamental law of physics, the conservation of angular momentum. Think of an ice skater. When she pulls her arms in, she spins faster. The solar nebula was the same. As it collapsed inward toward the Sun, its slow, random rotation concentrated and sped up, setting everything within it spinning in the same general direction. All those collisions, combined with heat from radioactive decay, turned the early Earth into a molten ball of rock and metal. In this superheated state, a crucial process called planetary differentiation occurred. Heavier elements like iron and nickel sank under their own weight to the planet's center, forming the dense core. Lighter silicate materials floated upwards, eventually cooling to form the mantle and the crust. This sorting process is what gave our planet its layered structure, a structure that's essential for everything from our magnetic field to plate tectonics. But the drama wasn't over. Our young planet was about to have its most violent day ever. A protoplanet roughly the size of Mars, which scientists have nicknamed Theia, came hurtling through the solar system on a collision course. The resulting impact was cataclysmic, an explosion of unimaginable scale that nearly obliterated the young Earth. This giant impact tilted our planet on its axis, giving us our future seasons, and blasted a colossal amount of vaporized rock into orbit. This ring of debris didn't just float away. Over time, gravity pulled it all together, forming a new celestial body, our Moon. This incredible origin story explains why the Moon is made of similar rock to Earth's outer layers. From a chaotic cloud of stardust and a series of violent collisions, our spinning, molten world, now with a constant companion, was finally born, ready for the next chapter in its epic journey. Think of an ice skater. When they pull their arms in, they spin faster. That's angular momentum. Earth works the same way. With no giant hand reaching out to stop it, Earth just keeps turning day after day. The only thing that can stop an ice skater's spin is dizziness. Thankfully, planets don't get dizzy. So if Earth has been spinning for billions of years, why hasn't it just stopped? The answer lies in a principle called conservation of angular momentum. Think of Earth as a colossal spinning top. Once set in motion in the near frictionless vacuum of space, it tends to keep spinning. But it's not entirely without breaks, and the main one is our closest celestial neighbor, the Moon. Shouldn't Earth have slowed down by now? It has. Just a little. Tides caused by the Moon create friction that very slowly slows Earth's spin. The Moon's gravity doesn't just pull on our oceans. It also tugs on the solid planet, creating subtle bulges in the rock. As Earth spins faster than the Moon orbits, it drags these tidal bulges ahead. The Moon's gravity then pulls back on them, creating a constant, gentle braking force that generates immense friction. This process is incredibly gradual, but over geological time it adds up. We have fossil evidence to prove it. By studying the daily growth rings on ancient corals, scientists know that about 400 million years ago, a day on Earth was only 22 hours long. Today, it's 24. Our planet's rotation is currently slowing at a rate of about 1.7 milliseconds per century. An imperceptible change day to day, but a profound one over the eons. Projecting this forward, the trend will continue. Millions of years from now, it might be 25. But there's a fascinating consequence. As Earth's spin slows, that lost angular momentum is transferred to the Moon, pushing it into a slightly higher orbit. Right now, the Moon is drifting away from us at about 3.8 centimeters per year, roughly the same speed your fingernails grow. As our days get longer, the Moon gets farther away. This slowdown has a real-world impact on our modern timekeeping. Fun fact, scientists actually add leap seconds to our clocks sometimes to keep them in sync with Earth's gradual slowdown. Our global time standard, UTC, is kept by incredibly accurate atomic clocks, while another standard, UT1, is based on Earth's actual rotation. Because Earth is slowing, these two times drift apart. The leap second is a tiny adjustment that reminds us we live on a dynamic, ever-changing planet. Now imagine if Earth suddenly stopped. The atmosphere would keep moving at 1,000 miles per hour, creating winds that could flatten everything. Oceans would slosh across continents. Basically, it'd be bad news for everyone. Good thing physics won't let that happen. If the Earth did stop spinning, Mondays would feel even longer than they already do. The simple act of our planet spinning is the master conductor of life. Its most obvious gift is the rhythm of day and night. This 24-hour cycle has ingrained itself into the very biology of life, creating what scientists call circadian rhythms. Plants follow the sun for photosynthesis, while animals have evolved intricate patterns of sleep and hunting, all timed to the sun's daily journey. But the spin's influence runs deeper, stirring our atmosphere and oceans through the Coriolis effect. As Earth rotates, it deflects moving wind and water. This is why hurricanes spin in different directions depending on the hemisphere. This effect also drives the vast ocean currents that act like a planetary circulatory system, transporting heat around the globe and regulating our climate. Without this rotation, Earth would be a world of brutal extremes. One hemisphere would be locked in perpetual, scorching daylight, hot enough to boil water. The other side would be trapped in an endless frozen night. The narrow twilight zone between them would be ravaged by constant, ferocious winds as air rushed from the hot side to the cold. Life as we know it would be impossible. Crucially, our spin also generates Earth's protective magnetic field. The rotation of our planet's liquid iron core creates a shield that deflects harmful solar radiation. Without this magnetosphere, the sun's energy would strip away our atmosphere and bombard the surface. So from our daily schedule to our planetary shield, spinning makes Earth uniquely livable. And when you look at other planets, you see just how special our spin is. Jupiter spins so fast, one rotation every 10 hours, that it bulges at the equator like a squished basketball. This shape, called an oblate spheroid, is a direct result of its rapid rotation. Our steady 24-hour spin is truly a key ingredient in Earth's recipe for life. So why does Earth spin? Because it was born spinning out of a swirling cloud of gas and dust. Angular momentum keeps it going. The Moon is slowly slowing it down, and without that rotation, life as we know it wouldn't exist. This has been WhyOWhyTV. If you learned something new, give this video a like, share it with a friend, and subscribe so you never stop asking why. And here's your teaser. If Earth spins around the sun, why don't we feel it? That's a why for another time.